Okay, so in this video, we are going to prove the following theorem. So here are the assumptions. We let V be a vector space with dimension equaling n. So V is an n-dimensional vector space where n is some positive integer. If the vectors u1, u2 up to um, so those are m vectors, obviously from the vector space V, if those m vectors are linearly independent, automatically m must be less than or equal to n, the dimension of the vector space. So let's prove this, and you will see that the proof is essentially a copy-paste of the argument from the previous video in where we proved that given a vector space, any two bases must contain the same number of elements. So I'll go over the proof a little more rapidly. So let's see, we have an n-dimensional vector space, therefore we can take a basis of V that contains exactly n linearly independent vectors. So let B to the set V1, V2 up to Vn be a basis of the vector space V. And of course, the basis contains n linearly independent vectors because by assumption the dimension of the space was n, and by definition the dimension of a vector space is the number of elements of vectors in any basis. So we know that the span of B is all of V, and that the vectors v1 through vn are linearly independent. So you say, okay, well, what does that mean? It means that if we take all possible linear combinations of these n vectors, that is by definition what the span of B is, we can generate the entire space V. Well, because these vectors are vectors in V, we can express every one of them by a linear combination of these n basis vectors. Well, let's express u1 as a combination of these vectors. So u1 has to be some linear combination of the vectors v1 through vn. The question is now, is it possible that every coefficient c1, c2 through cn is equal to 0? Well, think of it. If every coefficient was equal to 0, this combination would be the 0 vector, therefore u1 would be the 0 vector. But if a set contains the 0 vector, it is automatically linearly dependent. So because by assumption the vectors u1 through um are linearly independent, u1 cannot be the 0 vector, so at least one of the coefficients must be non-zero. Whichever one it is, you can move it up front instead of c1, and so we can assume that c1 is not 0. So we can solve for v1, right? Send these on the other side. So c1 v1 equals u1 minus c2 v2 minus dot 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 up to cn vn. Since c1 is not 0 by assumption, we can multiply across by 1 over c1. And so we get that v1 ends up being 1 over c1 u1 minus c2 over c1 v2 minus up to cn over c1 vn. And why is this interesting? Well, look at this. If you have vectors u1 and then v2, v3 up to vn, you can generate vector v1, as v1 is a linear combination of vectors u1, v2 up to vn. So if you replace v1 by vector u1, you lose nothing, because with u1 and v2 up to vn, you can generate v1. And so the span of u1, v2 up to vn will also be equal to v. And that is a copy paste of the argument we used in proving that any two bases of a vector space must contain the same number of vectors, of elements. And you think of it, well, why stop there? We can repeat the argument, right? u2 is a vector in V, and these n vectors generate the entire space, and so u2 is a linear combination of these n vectors. As these vectors are linearly independent, when we express u2 as a combination of these vectors, one of the coefficients of the v's must be non-zero. We can assume it's the coefficient of v2, and so we can express v2 as a combination of u1, u2, v3 up to vn. And so we could use the same argument to say that the span of u1, u2, and then v3 up to vn is also the whole space V. So if we just use the same argument, and this is again a copy paste of the previous video, the span of u1 replacing v2 by u2, and then v3, they stay the same up to vn. This is still the entire vector space V. But now think of it. Now we just repeat, right? We're going to try, well, not try, but succeed in copy pasting the argument and showing that if we replace v3 by u3, the span is still all of V. And so we keep repeating this. And the question is, can we fit all of these vectors into the basis P? Do we have enough V's that we can replace v1 by u1, v2 by u2, and so we won't run out of V's? And again, the idea is, let's assume that we actually run out, that there are more vectors u, so m is strictly bigger than n. And then we'll have a very easy contradiction, right? So if m is strictly bigger than n, then if we repeat this argument n times, in the end, v1 is replaced by u1, v2 is replaced by u2, v3 is replaced by u3, up to vn is replaced by un, and the span is still equal to V. But if you think of it, if m is strictly bigger than n, and we had m vectors in the u's, u1, u2 through um, well, clearly um is not there. So um does not belong to this list. But now think of why this is a contradiction. Because these n vectors, u1 through un, span the entire vector space, and um is a vector from V, um must therefore be a linear combination of the vectors u1, u2 up through un. But if um is a combination of the previous vectors, we know that by definition this implies that the vectors are linearly dependent, right? This is something that we proved. Vectors are linearly dependent if and only if at least one vector is a linear combination of the others. And so if m is strictly bigger than n, um is not in this list, but these vectors span the whole space, and so it is possible to express the vector um as a linear combination of the vectors u1, u2 through un, and therefore these vectors are linearly dependent because um is a combination of the previous vectors. And that is the implication here. And we have a contradiction, because by assumption, the vectors u1 through um were linearly independent. So this is our contradiction. And so what went wrong here? We assumed that m was strictly greater than n, and we obtained a contradiction. Therefore, this has to be false. Well, what is the opposite of m being strictly larger than n? It is m is less than or equal to n. And this was what we were trying to prove. We said that if we have an n-dimensional vector space, and we have m linearly independent vectors, m must be at most n, the dimension of our space. And there you have it. This completes the proof. And now there is a really nice corollary of this. So now think of it. Suppose that we have a subset of a vector space. So say if the vectors u1, u2 up to um are all inside the vector space V. So therefore, as a set, this is a subset of V. And assume that we have more vectors than the dimension of V. So an m is strictly greater than the dimension of V. The conclusion is that these vectors must be linearly dependent. And think of why we already have proved this in the previous result. Think of it by contradiction. The conclusion here is that the vectors are linearly dependent. Well, assume that they weren't, right? The assumption here is that we have m vectors in the vector space V, and that m is strictly bigger than the dimension of the space. Well, assume that these vectors were linearly independent. So we can quote the previous result. If we have m linearly independent vectors, m must be at most the dimension of the space. But that is a contradiction because we assumed here that m was strictly greater than the dimension of the space. And that's a contradiction. You see, if these vectors were linearly independent, m would have to be less than or equal to the dimension of the space. As it is not the case, our assumption is faulty, so these vectors cannot be linearly independent, therefore they must be linearly dependent, and that's the proof. And why is this useful? Well, think of it. Sometimes the question will be to decide whether or not vectors are linearly dependent or independent. If you ever have vectors in a vector space, and you have more vectors than the dimension of the space, you do not have to do anything. Automatically, these m vectors are linearly dependent. Let me give you a simple yet non-trivial example of this result. So always keep this in mind. If you have vectors, and you have more vectors than the dimension of your space, there is no work to be done. The vectors are automatically linearly dependent. So here's a simple example. Suppose we take the space P2. P2 is the set of all polynomials of degree at most 2 and with real coefficients. So we can have a constant term plus some multiple of x plus some multiple of x squared. where a0, a1, a2 are allowed to range over all real numbers. So all it is, as we have said, is the set of polynomials of degree at most 2. And now think of it. Let's extract from this a basis. If you write this down, this is a0 times 1, the constant polynomial y equals 1, plus a1 times x, this is the linear polynomial y equals x, plus a2 times x squared, this is the quadratic polynomial y equals x squared, and once again, and I'll be a little lazy here, ai is an arbitrary real number. But think of it. The space P2 is any multiple of 1 plus any multiple of x plus any multiple of x squared. So this is the set of all linear combinations of the elements 1, x, and x squared. This is by definition the span of 1, x, and x squared. And so you see that the vectors, the polynomials, 1, x, and x squared, form a basis of P2, or at least a set of generators. Let's prove that they actually also form a basis. We have to prove that these are linearly independent. Well, we go back to the definition. Let's consider a linear combination of these vectors. So c1 times 1 plus c2 times x plus c3 times x squared being equal to the 0 vector. Well, as our space is a space of polynomials, the 0 vector is the 0 element, which therefore is the 0 polynomial. This is equal to 0 for all values of x. But we know that to have a 0 polynomial, for every value of x, every coefficient must be equal to 0. So c1 must be 0, c2 must be 0, c3 must be 0, and you see that the linear combination of the polynomials 1, x, and x squared, giving the 0 polynomial, only has the trivial solution. Therefore, by definition, the vectors, the polynomials 1, x, and x squared, are linearly independent. And so we have a basis. These are generators of the space, and they are linearly independent, and so they form a basis of P2. So the set B, 1x x squared, is a basis of P2. Okay, so if we ask, well, what is the dimension of P2? Well, the answer is obviously 3. The dimension of a vector space, and again I'm leaving, and if you think of it, this is quite nice, right? We could have asked, prove that P2, the set of polynomials of degree at most 2, is a vector space, and you could have used here the subspace theorem, because this is obviously a subset of the vector space of all functions, so you would have had to prove closure under addition and scalar multiplication. But as we have proved that P2 is the span of 3 vectors, and we know the span of any number of vectors is always a vector space, this simultaneously proves that P2 is a vector space. And as always, the dimension of a vector space is simply the number of elements in any one of its bases, and here we have 3 basis generators, 3 generators I should say, so therefore a basis contains 3 elements, and so P2 is a 3-dimensional vector space. And now here's our application of the previous corollary. Here's my question. Or let's just look at it as a claim. Suppose I ask you to determine whether or not the vectors were linearly dependent or independent. Of course, here we have a space of polynomials. The vectors will be polynomials. So suppose I gave you the polynomial x minus 1 x squared plus 7x minus 3, 3x minus 5, root of 2 x squared minus 8x plus 17. And I ask you, are these polynomials linearly dependent or independent? Well, you could fall back to the definition, right? Consider a linear combination of these four polynomials and check if you have only the trivial solution being giving the zero vector. If you only have the trivial solution, they are independent. If you can find a non-trivial solution to these vectors giving the zero vector, then they are linearly dependent. But here we can do much simpler. Think of it. We have four polynomials, and you can view this as a set of vectors, right? Now this is a linear polynomial. This is a quadratic, linear quadratic. And so we have four polynomials, but they are all inside of P2, right? P2 is a set of polynomials of degree at most 2. Every one here is of degree at most 2. So all of these, if I call this set, say, S, are in P2, so S is a subset of P2. But the size of S is 4, which is strictly bigger than 3, and that is the dimension of your space. So, if you have more elements than the dimension of your space, automatically these polynomials are linearly dependent. So as a set, S is linearly dependent. So no need to consider linear combinations of these four polynomials being equal to the zero vector and trying to solve for the coefficients. As we have four polynomials living in the vector space P2, and that is a three-dimensional vector space, and as we have more vectors, elements, than dimensions, automatically the set is linearly dependent. And that's it. And you will see sometimes I will say to use a dimension argument, and that is the argument I'm referring to. If you ever have a vector space and a subset of the vector space, if you have more elements than the dimension of your space, the elements are automatically linearly dependent. And again, that is what I call a dimension argument.